All right, we are back. So we just calculated the wavelength going from n equal to 1 to n equal to 0. But you could also have a drop from n equal to 2 to n equal to 1, from n equal to 3 to n equal to 2. What other possibilities? Well, you could have n equal to 3 down to n equal to 2, n equal to 3 down to n equal to, n equal to 3 down to n equal to 1, excuse me, n equal to 3 down to n equal to 0. I mean, these are all possible, okay? And you can calculate the energy drop in the electron and go through the same process to figure out the energy gained, the energy of the photon that is released, and then the wavelength of that photon. Notice that they're very specific values. This is that whole quantum concept. They're quantized. So they exist in very specific quantities. They're not just random. Going back to that flame test you most likely did in chemistry when you're looking through this handheld spectroscope that has a diffraction gradient in it, and you look at a flame and you see specific lines for a certain chemical. Where do those lines come from? The light, lines of light. This is where they come from. You don't just get the entire spectrum of colors. You only get very specific lines at very specific places. They come from, you have all these things going on at once usually, because there's a whole, you don't just have a single electron dropping. You have a zillion electrons, right, going on in that flame, that whatever that chemical is. And they're doing all these possible combinations. So you see the wavelength that goes from 3 to 2. You can calculate it out and see that one. You're seeing it from every single drop. Now, of course, you don't see the ones that are in the ultraviolet range. I mean, we can detect them other ways. But you can see the ones that are in the visible spectrum. Let's just look at one more. So let's say we're talking about from, I don't know, let's just look at from 3 down to 1. So if an electron goes from n equal to 3 down to n equal to 1, or it's just going to go through the exact same process. So from n equal to 3, can you see that? Yeah. From n equal to 3 down to n equal to 1. Well, at n equal to 3, it's at negative 2. So we're going to first calculate the change in the energy of the electron. And that's going to be, it's always final minus initial. So n equal to 1 is negative 9. And that's where it ends. It started at 2, right there. So that's minus a negative 2. So that is negative 7 electron volts, right? Right. That's the change in energy of the electron. Where does it, when you have a change in energy, the energy goes somewhere. So what's the energy of the photon given out? Oopsies. The energy of the photon is minus the change in the energy of the electron. So that's going to be minus negative 7 is 7 electron volts. And then you can calculate the wavelength of that. So if you calculate the wavelength that corresponds to this specific photon that went from here to here, then using that equation, remember that equals hc all over lambda, and so lambda, again, I want to be sure you can still see this. Yeah, lambda equals 1240 all over 7. It's going to be not too far off from that. So 1240 divided by 7, which is 177 nanometers. Okay. I think it's pretty cool that we're able to actually calculate this stuff. I mean, you think about that. That's pretty neat. And it's really not that hard to understand. So this is called the emission spectrum. Emission spectrum for a specific chemical. Emission spectrum. Emission spectrum. Those are the photons that are emitted from that specific chemical. The flip side of this is the absorption spectrum. So you pass white light through a gas, a specific gas, whatever it is, all right, carbon dioxide, whatever. You pass, or oxygen, pass white light through it. Well, on the other side, what comes out on the other side? Most of the light comes out, except for those specific photons that have this energy range. For example, so this is just this whole process in reverse. If you have the absorption spectrum, it's the whole process in reverse. You are passing white light through, and most of the light passes through except for the photons that have the same energy as the energy differences here. Those are absorbed, kicking the electrons up to a higher state. So if you pass white light through and you have a photon that's at 6 electron volts, that's not going to make it through the gas, because that gas, that chemical, is going to absorb 6 electron volts, because that's from here to here. So it's going to absorb that, and it's going to jump up. Okay, it's going to, the electron is going to jump up, and that color of light is out of the equation. It's out of the light that's passing through. So you wouldn't detect it on the other side. You'd see most of the other colors except that one. You also wouldn't see any photon that had a wavelength of 177 nanometers, an energy of 7 electron volts, because that's absorbed here. You also wouldn't see anything that had, what is the difference here? 5 electron volts from 4 to 9. You wouldn't see anything that had an energy, a photon that had an energy of 5 electron volts, because that would be absorbed by any electron that's right here, causing it to jump up to here. You wouldn't see anything that had 2 electron volts, because an electron here would absorb that and jump up to there. And what's the last combination? I guess from 2 to 15, which is what, 13 electron volts, that photon would be absorbed and taken out of the white light. And then you're looking at it as it comes out of the gas, and you see all the other colors except those. You'd see little black lines at the spots where these photons were all taken out. All right. That's called the absorption spectrum. Absorption. It's the exact same process in reverse, where white light is passing through the gas, and these specific photons are being absorbed. The photons are being absorbed, kicking up the electrons to a specific energy. Now, one other thing before we finish. It takes 15 electron volts to get an absorption of a photon at 15 electron volts to get this to get an electron to leave from the ground state. What about 16 electron volts? It's fine. Once you get above 15 electron volts, and an electron can absorb 16 electron volts. It takes the 15, and that extra electron volt is kinetic energy. All right. So it would have 15 electron volts required to leave the atom, plus 1 extra leftover electron volt of kinetic energy, and it would travel away. What if you had 20 electron volts? So you had a photon at 20 electron volts traveling through. It travels through a gas, or it hits a metal, or whatever. It hits an atom. Of the 20 electron volts, 15 electron volts would be required to ionize it, in other words, to get that electron away from the atom. But you still have 5 electron volts left over, right? So that's kinetic energy. Goodbye. All right. An electron traveling all on its own, it's no longer attached to an atom. It has kinetic energy, and that's what's left over. All right. That's it for atomic physics.